Oh yeah?
I was going to suggest
It looks like the same one they give out for St. Patrick's Day, but it's a different shape.
I was going to
But
suggest
it goes
Instead of
leprechaun.
a shamrock. There we go.
Right.
You're not the only one.
Thanks everyone for coming today. We have Otar Sepper giving the talk today. Last week he talked a little bit about the orientation of the magnetic field and how that affects superconductivity in chains. So now we're going to hear a little bit more. So thank you.
Thanks. Last Friday I presented an unusual case where the low temperature superconductivity showed unconventional behavior. And now I'm going to talk about yet another very interesting and puzzling case. And that is of the quasi-one-dimensional layered superconductor, which is called the purple bronze. Its chemical formula is here. It's in lithium molybdenum oxide. And it's a transition metal oxide. It's a layered, highly anisotropic metal. And it is a strong candidate for the triplet type of superconducting pairing, which I'm going to discuss in this talk. So let's review a few facts on unconventional superconductivity. So we know that superconductivity is destroyed when Cooper pairs are broken. And it is a common knowledge that magnetic field is the enemy of superconductivity. Right? Magnetic field destroys it. But there are two mechanisms involved, because the magnetic field acts through Lorentz force on electrons' charge, but it also can exert torque on the spin of electrons. So in the first case, in the case of the Lorentz force, we can think about the destruction coming about through the orbital frustration of the order parameter. And in the second case, the spin-splitting effects is due to the fact that the magnetic field tries to align the spins of the Cooper pairs. So in the conventional BCS superconductor, Cooper pairs are in a singlet state. And so let's go back to our basic quantum mechanics, addition of angular momentum. So total spin is 0 in a singlet state, and this is a BCS Cooper pair. So magnetic field will try to align the spins, and therefore it will destroy the superconductivity. In the triplet state, we have three possible choices. And one of them is a linear combination of down-down and up-up, which is not sensitive to paramagnetic spin-splitting effects. So, although there is a state that is sensitive like this, right, with spins anti-aligned, if we choose a linear combination of up-up plus down-down, we are in the S1 triplet state, and the Zeeman effect is moot. It doesn't play a role anymore. So how do we actually calculate the magnetic field, the minimum value of the magnetic field that will align the spins and destroy superconductivity? Well, we can get an estimate by setting the Zeeman energy splitting between the energy levels to greater than the superconducting condensation energy, which we can think about as being sort of a binding energy of formation of a Cooper pair. So when we set them equal to each other, we can numerically, in fact algebraically here, extract this paramagnetic limiting magnetic field. So here chi n is just the normal metallic state polysusceptibility. So it has this electron G factor, which is about 2, Bohr magneton, and the density of states at the Fermi level. And delta 0 here has been set to the BCS value, which is a well-known result. It's 1.76 kBTC. And Tc is just the superconducting transition temperature in zero field, right? So we can solve this algebraically and extract a value of about 1.84 Tc Tesla per Kelvin. So what this means that since we're dealing here with low temperature type 2 superconductors, they have a TC of between 1 and 2 Kelvin. So you get the spin splitting field of about 2 to 4 Tesla. Right? And this result is for an isotropic 3D superconductor, which is not exactly the case of our example, but it gives us a rough estimate. In fact, for a lower dimensional superconductance, this result is even lower than it. I think it's 1.5 on the order of that. So this is a magnetic field versus a temperature diagram for this purple bronze. So we see here a very puzzling situation because as we approach 0 Kelvin, all the fields along all the crystallographic axes tend to saturate, and in particular the field parallel to the most conducting axis. Right? This is a quasi one-dimensional crystal. We take the x-axis to be the most conducting axis. Tends to saturate at 15 Tesla. But the paramagnetic limit lies somewhere here, because TC for the purple bronze is about 2 Kelvin. So if it was a singlet superconductor, we would expect superconductivity to be destroyed by Pauli effects around 3 Tesla, yet the field is all the way over here. So that presents a question, and we put forward this compound as a novel candidate for this rare phenomenon of triplet pairing in unconventional superconductivity. Now, there are several, yes?
Sorry, I don't quite understand this plot. On the y-axis, that's the field that destroys conductivity?
Yes, as a function of temperature. So the y-axis is the magnetic, it's the externally applied magnetic field on this crystal versus temperature at which superconductivity is destroyed. So above this curve, you can think about this as being the resistive state, in fact, normal metal, and below this curve, you have superconductivity. And this curve is like the boundary at which superconductivity, so it gives us the transition, so the transition field to go from superconducting to a normal state. Right? So this value is in Teslas, this is in Kelvin. Now, so there are several any questions?
I have a question.
Yeah.
So what did you say about that? Why it should be triplet? Because what is...
So I'm saying that if it was a singlet superconductor, when you reach a value of about 3 Tesla in externally applied magnetic field, the spins would align. So it would be energetically unfavorable because of the Zeeman splitting to stay in a superconducting state. And that would happen at 3 Tesla. So we wouldn't see this high limit here, saturation limit. Superconductivity would be destroyed much earlier than that. But the fact is that this experimental plot shows that it doesn't do that. So a proposal by the experimental group, this experimental group, and then our theoretical proposal, we state that this is a strong candidate for a possible triplet type of pairing, right? But now I have to mention that there are several factors which can suppress this Zeeman splitting, right? Suppress in terms of prevent it from aligning and make the field actually higher than HP. So what are some of the possible...
What are the 3 colors, the 3 curves?
So this one is the field along the most conducting axis of the crystal, the x-axis. These are the fields of the other perpendicular directions, the y and the z. These have been actually scaled by a factor of 3 and 12. So if you were actually plotting on this diagram, they would saturate around 4 Tesla, both of them, because it's, and this one would saturate around 1 Tesla. You see, the red one is parallel to the y-axis, and it's scaled by a factor of 3. So 12 divided by 3 is 4. So the magnetic field along the y-axis saturates around 4 Tesla, around the z-axis around 1 Tesla. But we're not considering these. In my talk, we'll talk about this intriguing case, because it's much higher. In fact, it's 5 times higher than the paramagnetic limit. I also have to mention the fact that the formula for the paramagnetic limit that I presented here is for a 3D superconductor. But in this case, the value of about 3 Tesla has been experimentally determined from the actual numerical values of the Pauli susceptibility and the specific heat discontinuity and so on. So it's an experimentally extracted result, and it's 3 Tesla, and it's 5 times lower than the maximum field theory. So we have to resolve some serious inconsistencies if we assume that this is a regular spin singlet type of pair. So far? Good. Okay, so what are the factors that can suppress the Zeeman splitting? One is so let's go over this first. So one is the spin orbit scattering. It seems that this material has very little effect coming from impurities. It has been measured experimentally, and the mean free path has been extracted, and it looks like the spin orbit mean free path is 2 orders of magnitude greater than the Boltzmann transport length. So it's a pure the superconductor is in a pure limit, so spin orbit scattering is almost negligible. Another possibility is the so-called the loft state. Now, this is a special case where the Cooper pair acquires a non-zero net momentum, and the electrons paired on Fermi surfaces, the Fermi surfaces actually shift with respect to one another. And that results in the suppression of Zeeman splitting, so superconductivity can persist for fields that are higher than the Pauli limiting field. We have specifically calculated the limiting field for this case, and it turns out to be about 5 to 6 Tesla, which is still 3 times smaller than what we're observing experimentally. Now, what are the counter-arguments? The counter-arguments are that, so some of the factors that can suppress orbital frustration. Remember, orbital frustration, we're talking about type 2 superconductors where you have the Aberkosov vortices penetrating the superconductor, and eventually when the superconductor gets saturated with them, you have a resistive transition. Certain things can suppress that, and one is the so-called dimensional crossover, which happens at high magnetic fields. And it's actually not too difficult to understand. So we're thinking about this superconductor as a layered material, right? With conducting planes, these chains are in the conducting planes, and the layers are separated by some lattice constant, right? So if I could just quickly show you, if we have the Lorentz force, remember the magnetic field, so these are the chains along the x-axis, and in our case, we're taking the magnetic field H along the x-axis, so the Lorentz force is minimized because charge is moving parallel to the field. So if we write the quasi-classical Newton's law type of equation for the Lorentz force, dp dt equals just v cross h, and v here is just the Fermi velocity. And Fermi velocity is constant approximately along the chain, so we have Pz equals E over C V Fermi ht. And then in the crystal, from the tight binding approximation, right, we have the energy dispersion relation of the form 2Tx cosine P times some lattice constant A, right? And then you have Vz from Hamilton's equations is just dE dP. In this case, it's actually Tz here, Pz. And there are other terms with Tx, and Ty, but the velocity, this is the perpendicular velocity, right? The velocity of essentially hopping between the conducting planes. So just take the derivative of this with respect to Pz, and you will see it's 2Tz Az times sine, with a minus or something like that, right? And then Pz is here. We can substitute that into here, and then simply integrate once with respect to time, so we get z of t. And z of t is just a quasi-classical electron trajectory with a typical cyclotron frequency omega. So if you integrate this, right, you have something of this form: 2Tz over omega z cosine omega z t, where this interplane cyclotron frequency is E, H, V Fermi, Az over C. H is the magnetic field. So you can see that when the magnetic field is very large, this ratio becomes smaller and smaller, and therefore the electrons are confined to these two-dimensional planes. So the flux through the superconductor essentially doesn't kill the Cooper pairs, because now they are, so this is what's called dimensional crossover. Because the amplitude is inversely proportional to the magnetic field H. If we make H very large, we essentially get 2D superconductivity. So in a crystal like this, right, electrons are confined through the to the two-dimensional plane, so the magnetic field essentially has no flux on a flat plane.
You said earlier that the charge is confined, it moves in the direction parallel with the applied field? It can't move perpendicular?
Well, this is quasi-one-dimensional. We have Fermi velocities in all directions. The most conducting axis has velocity v Fermi, what I'm calling v Fermi, in the x direction, and there are also perpendicular velocities as well. The point is, those perpendicular velocities are very small. So I'm neglecting them in this approximation for the purpose to demonstrate what is the dimensional crossover. In fact, dimensional crossover does not happen in our case. But if it did, it could suppress orbital pair breaking effect. Another effect that can suppress orbital pair breaking is the Landau level quantization at low temperatures and high magnetic fields. And so when a single Landau level is occupied, essentially superconductivity is only limited by impurity scatterings and Zeeman splitting and so on. This result is by Sanovich, which is Ina's husband, who passed away, unfortunately. Okay, so let's go on. My declaration is that triplet superconductivity is a rare phenomenon. That's why this candidate, the purple bronze, is an important novel material. So our motivation, in general, is that detailed spatial orientation studies of the upper critical field are very important because they can reveal the unconventional pairing nature of the superconducting state. Also, from a general standpoint, there are a lot of anisotropic compounds, organic superconductors. Triplet pairing has been firmly established in the compound uranium-platinum-3, and the famous perovskite superconductor, the ruthenate, it's highly probable that it exists in this compound as well. So these exotic phases are very important, especially for these highly anisotropic compounds, to study from a theoretical point of view. Earlier studies on organic superconductors, in fact, show the upper critical fields being greater than the permagnetic field. And, for example, NMR measurements on this PF6, this is an organic superconductor, which is one of the Beachcar salt families. So the NMR measurements of night shift showed that the PF6 case is a possibility for triplet pairing, and the chlorine-oxygen 4 is actually a spin singlet. So there's a lot of stuff going on there. But here's what they have measured experimentally. This is resistivities. So if we look at it, resistivity in the x direction, the one we're interested in here, is rho b. And this is, so what we see here is, so you can see the high anisotropy, right? Resistivities are several orders of magnitude greater than the most conducting, smaller than the most conducting axis resistivity. So perpendicular direction is 2,000 times smaller than the x-axis. So it shows a metallic behavior until about 15 or so Kelvin. This axis should have a temperature in Kelvin, sorry about that. So this is resistivity in microohm centimeter, but this axis should be temperature in Kelvin. So metallic behavior down to about 15 Kelvin. Then there is an upturn in resistivity, which generally characterizes a lot of these one-dimensional compounds. So it shows a kind of an insulating phase between 15 Kelvin, and then a sharp drop, superconductivity at about 2 Kelvin. This inset here is the magnetoresistance, and it shows a quadratic behavior with the applied magnetic field. Now this is important because the slope of this curve from the Boltzmann transport equation, it can give us the mean free path. We can estimate it to be about 600 angstroms. And actually Abrikosov's formula relates the spin orbit mean free path to Boltzmann mean free path as z over 137, which is the fine structure constant, to the power 4. And z is the, for molybdenum it's about 47. So we get that the spin orbit mean free path is 2 orders of magnitude longer in this case. So it's essentially it's impure, no impurities in this. And also an important number here to look at is the parallel coherence length. Now last time I talked about coherence length, you can roughly think about it as a length scale on which superconductivity varies spatially. You can also think about the Cx as the typical size of a Cooper pair. So again, this number turns out to be comparable but smaller than the Boltzmann mean free path here. So we propose a new candidate for triplet superconductivity. This is a summary of the facts in favor. The most important one is that we really cannot account for such a large critical magnetic field, even if we somehow magically combine all the factors such as spin orbit coupling, maybe some electron-phonon coupling in a strong limit. The renormalized values would bump up HC2 maybe to twice the value, but not 5 times the value of 15 Tesla. And again, the paramagnetic limit has been experimentally determined. It does not depend on any kind of theoretical model. So, previous arguments against triplet pairing, and this is an important point, is that the field here is parallel to the most conducting axis. The Lorentz force is minimized. So orbital effects are insufficient to destroy superconductivity, and therefore it could only come from paramagnetic spin split. Our non-trivial theoretical result, that superconductivity can in fact be destroyed by pure orbital effects, even when the magnetic field is parallel to the most conducting axis. One of the requirements in this case is that superconductivity, the planes, the conducting planes are well coupled. So the coherence length is greater than interplane separation, which we actually show that is well satisfied in the purple bronze. So let's see how much time I have, about 10 minutes. So we start with the tight binding approximation for the crystal. This is the quasi-1D Fermi surface. You see it's two open sheets with slight warping. So we'll take electrons with spin up and spin up to be paired like this on opposite Fermi surfaces. These are the quasi-1D chains, layers. The magnetic field is parallel again. So based on this kind of linearization, so remember here the hopping, right, integrals are different in this compound by orders of magnitude. So because Tx is much larger than Ty, much larger than Tz, we're able to linearize the anisotropic electron spectrum on this sheets of the Fermi surface this way, and then we get the Hamiltonian, which is obtained through a standard procedure by parallel substitution. Essentially, you make this canonical transformation for the momentum. You obtain a Hamiltonian, and we include the spin interaction here. Mu b is the Bohr magneton, sigma is value of electron spin plus minus 1. So with this Hamiltonian, in a quasi-classical approximation, we can find the exact wave functions for the electron motion in a parallel magnetic field. So we have these exact wave functions, so we can construct the finite temperature Green's functions. The Green's functions satisfy this equation here, although I think I made a mistake, should be here H0, which is just the orbital part of the Hamiltonian. And omega n is just the fermionic Matsubara frequencies here. Sorry, I'm trying to rush through to fit everything. So through Garkov's equations for unconventional superconductivity, our goal is to obtain the order parameter, which is going to be an integral equation called the gap integral equation. The solution of this equation, delta y, is typically called the superconducting nucleus. This is the diagrammatic representation of it here. G is called the electron coupling constant. We effectively eliminate it from the theory. So we calculate the kernel here for the integral as a product of Green's functions, and you can see that we include the triplet pairing in the form of up-up plus down-down states. And we arrive at an integral equation for triplet superconductors, which is specifically insensitive to paramagnetic spin splitting effects. So this is our general theoretical derivation. Now, some of the properties here. This integral equation is very general because it incorporates the quantum effects at high magnetic fields and low temperature regimes. These effects cannot be neglected when T is too low. The result of electron Bragg reflection from brilliant boundary zones cannot be neglected. This equation incorporates those effects. Now, it also incorporates the description of anisotropic 3D superconductivity. That's when the planes are well coupled. In the opposite extreme, when electrons are confined to 2 dimensions, you get kind of a Josephson coupling between the planes. That is called the Lorentz-Doniak model. It is included in this equation in the appropriate limit. We can show by expanding this equation near the critical temperature that we actually recover the standard Ginzburg-Landau limit as well. And our intent is to solve this equation under the appropriate experimental conditions which have been specified for the purple bronze in their measurements. The conditions are as follows. The experimental temperature is of the order of 0.5 Kelvin. It's about an order of magnitude greater than the special temperature at which the quantum effects become important. So this diagram here shows the so-called reentrant superconducting phase. So if you go back to that experimental plot, what should happen is this curve should just approach this y-axis here and saturate. But what happens is that instead of approaching the y-axis here and saturating, it goes up and re-enters into a high field superconducting regime. That's this case, when there is a dimensional crossover. So superconductivity now exists on the planes. Orbital effects do not suppress it. But in our case, we're working at higher temperatures, so quantum effects can be neglected. And we extract all the relevant band parameters and superconducting parameters. So A are just the lattice constants. The C here are the coherence lengths along all perpendicular directions. The electron hopping terms, T, have been calculated from Ginzburg-Landau relations. And we can see that CZ, 20 angstroms, is greater than the lattice spacing. So this is very important, because although in its normal state, non-superconducting state, this compound is one-dimensional, it seems that in its superconducting state, it's described by 3D anisotropic superconductivity because of this fact. That allows us to reduce the gap integral equation to this form and tend it to numerical analysis this way. The solution is this. It clearly shows unconventional behavior. This is nothing like the Ginzburg-Landau case where you have Gaussian smoothly decaying exponentials. So you have decaying oscillations here. The scale of these decaying oscillations is, the distance scale, is in fact on the order of the coherence length. And we calculate the magnetic field. So, this is our important result. The red curve is our theoretical calculation. It shows that indeed for a parallel magnetic field, superconductivity is destroyed at around 15 Tesla, and it fits experimental data pretty well. We went until up to about 1.5 Kelvin for our calculation, and down to about 0.06 Kelvin, after which quantum effects become important, but you can extrapolate the saturation point to be about 15 Tesla. So good quantitative agreement with experimental data, and we didn't use any kind of parameter fitting here. The only thing we used here is the value of the Ginzburg-Landau slope of their measurements. So we didn't vary any kind of parameters to fit this data at all in our theory. So to summarize, most importantly, our result is quite general. It shows that in quasi-1D compounds, superconductivity can be destroyed by pure orbital effects, even when interchain velocities are small. Purple bronze, lithium molybdenum oxide, shows many signs in favor of triplet pairing, and it would take an extraordinary coincidence of factors to suppress Zeeman splitting enough to account for such a high magnetic field, which we don't think is possible. And there is an excellent quantitative agreement between our theory and the recently measured experiments. Thank you.
Why not go to higher temperature with the calculation?
Calculations become difficult. The integral convergence becomes quite difficult at those.
It takes a long time for your computer to solve it. So.
It takes essentially a long time to solve it, yes, but the point is that we do expect deviation from this behavior at higher temperatures as we approach the Ginzburg-Landau limit near TC. But most importantly, at low temperatures, it shows the saturation which is important for triplet case.
So do you assume anything in this model when the pair is triplet?
So
In this model, when you calculate this, do you have anything when the pair is triplet? Right?
there are no assumptions besides the fact that magnetic field is parallel to the conducting chains, and that's about it.
So it does that the HC2 is very high, that makes it. That, just the fact that HC2 is very high, that implicates that it's triplet.
The fact, the combination that HC2 is 5 times bigger than HP, and the fact that this HC2 is parallel to the chains. Because the parallel case is difficult in the sense that because the interchain electron velocities are small, the Lorentz force is 0. I mean, when you have V cross B to be 0, Lorentz force is 0. So the counter argument was you cannot destroy superconductivity with a parallel field. The only thing that can kill it is paramagnetic effects. But as you can see, parallel effect, orbital effects can frustrate the order parameter enough to choke superconducting state out.
So, I think, so what favors the triplet pairing over the singlet, this thing?
We think that from a theoretical standpoint, electrons in Cooper pairs can be paired on opposite chains.
Right.
So when that's the case, repulsive interactions can lead to triplet
I
pairing.
get the fact that, I mean, if you have the anisotropy demands, the demands that there is a triplet pairing, but so you're saying that the singlet pairing and the triplet pairing also depend on the coupling between Cooper pairs in different layers.
The singlet and triplet pairing can be thought of as competing in phases. Right? So at very high fields, triplet pairing would be preferred because it's not sensitive to the paramagnetic spin splitting effects. Right? You can think about it this way. Because the superconductor shows such a huge discrepancy in magnetic fields, it's a strong candidate for such a type.